my name is Ekrem Berközant. I'm a computer engineering student. Today I will be representing my work for the Introduction to Autonomous Robots course, Project 1. The main objective of this project was to develop an simulation of an autonomous mobile robot using robot operating systems and gazebo. The critical challenge of this assignment was to achieve autonomous navigation and exploration without relying on a preset map. This means the robot must map the environment and navigate it simultaneously. Let me briefly explain the system architecture I designed for this project. I use Ubuntu 20.04 and ROS Nautic as the development environment. For the robot model, I selected the Turtlebot 3 Burger due to its compatibility with the navigation stack. The system consists of three main subsystems working together. First is SLAM, simultaneous localization and mapping. I utilize the Gmapping package. It takes laser scan data from the LiDAR sensor and odometry data to generate a 2D occupancy grid map in real time. Second is the navigation stack. I implemented the standard move-based node. This handles the global and local path planning, ensuring the robot avoids obstacles while moving towards a goal. Third is autonomous exploration. This is the core of my implementation. Instead of manually sending goals, I integrate the Explore Lite package. This package uses a frontier-based exploration algorithm. It automatically detects the boundaries between known and unknown space, called frontiers, and sends these points as goals to the navigation stack. Now let's look at the simulation results. Here you can see the robot in the standard Turtlebot 3 world. As you can see on the left side in RVs, the map starts completely empty. The green points you see appearing on the map representing the frontiers detected by the exploration algorithm. The robot autonomously selects the nearest frontier and moves towards it. While moving, the Gmapping node updates the map continuously. Notice how the robot successfully navigates around the hexagonal obstacles without collision. The local planner dynamically adjusts the trajectory to avoid hitting the walls. To test the robustness of the system, I also deployed the robot in more complex environment, the Turtlebot treehouse. This environment is challenging because it has narrow corridors, multiple rooms, and more complex obstacles. As you can observe, the robot systematically enters each room. Even in narrow doorways, the inflation-reduced parameters in the cost map allow the robot to pass through safely without getting stuck. It continues this process until no frontiers remain, meaning the entire house is mapped. During the development, I faced a few challenges. One major issue was the robot sometimes getting stuck in narrow corners or oscillating working the local planner. To solve this, I tuned the move base parameters specifically in inflation reduce and the cost scanning factor in the global and local cost maps. Additionally, I adjust the mean frontier size parameters in the exploration launch file to prevent the robot from chasing very small, insignificant gaps in the map, which improved the overall efficiency. In conclusion, I have successfully implemented an autonomous robot capability of exploring unknown environments without a pre-saved map. The robot successfully generated complete maps for both the simple world and the complex house environment. Thank you for listening. The source code and project reports are available on my GitHub repository.